October 18, 1917, Springfield Armory, Massachusetts. The demonstration had gone catastrophically wrong. Smoke still hung in the testing room, where the prototype heavy machine gun had just disintegrated during its first live-fire test. Twisted metal fragments lay scattered across the concrete floor, some pieces embedded in the reinforced walls. The Army Ordnance Board observers were already gathering their notes and preparing to leave, their expressions making clear what their official report would say. Another failure, another wasted appropriation, another weapons project to be terminated. But John Moses Browning, 52 years old and already the most successful firearms designer in American history, stood motionless before the wreckage, his weathered hands clasped behind his back, his eyes studying the destroyed weapon with an intensity that made the departing officers uncomfortable. His assistant, Frank Burton, approached cautiously, speaking in a low voice meant only for Browning's ears. "Mr. Browning, sir, the Ordnance Board is calling it a complete failure. They're recommending immediate termination of the heavy machine gun program. Colonel Thompson said your design is, and I quote, mechanically unsound, dangerously overpowered, and fundamentally incapable of sustained fire." Browning didn't respond immediately. He walked closer to the destroyed prototype, crouched down, picked up a fragment of the bolt assembly, turned it over in his hands, studying the metal failure with the focused attention of a surgeon examining tissue samples. Finally, he spoke, his voice calm, almost conversational. "Frank, do you know what I see here? Everyone else sees failure. I see a weapon that almost worked. Almost is the most important word in engineering. This gun fired 47 rounds before catastrophic failure. 47 rounds of 50 caliber ammunition, each round generating chamber pressure that would have destroyed any existing machine gun on the first shot. We're not seeing failure. We're seeing the birth pangs of something unprecedented." Burton glanced nervously toward the departing ordnance officers. "Sir, with respect, the Army is about to cancel funding. Without military support, we can't continue development. The war in Europe is consuming every available dollar. They're not going to fund what they're calling a ridiculous pipe dream." Browning stood, still holding the metal fragment, a slight smile crossing his weathered face. "Then we'll make them believe it's not ridiculous. We're going to build a machine gun that fires 50 caliber rounds at 600 rounds per minute with absolute reliability. We're going to create a weapon so devastating that it changes the fundamental nature of warfare. And we're going to do it in less than 12 months, because that's how long we have before the Army forgets we exist." What the assembled officers didn't understand, what Burton was just beginning to grasp, was that John Moses Browning had already solved the fundamental problem in his mind during the 47 seconds the prototype had functioned before exploding. The issue wasn't the concept or the caliber or the ambition. The issue was a timing sequence in the bolt mechanism, a fraction of a second discrepancy that created cascading stresses. Browning had identified the problem, conceived the solution, and was already mentally redesigning the weapon while everyone else was writing failure reports. The story of how a Utah gunsmith's ridiculous idea became the M2 Browning 50 caliber machine gun, the most successful heavy machine gun in history, the weapon that would serve continuously from 1933 through the present day, 90+ years without substantial modification, began not with that spectacular failure, but with a question Browning had asked himself 5 years earlier in 1912. What happens if you scale everything up? John Moses Browning had been born January 21, 1855, in Ogden, Utah Territory, the son of a Mormon gunsmith who had crossed the plains with Brigham Young. By age 7, John was working in his father's shop. By 13, he had built his first firearm from scrap metal. By 24, he had patented his first design, a single-shot rifle, so elegantly simple that Winchester Repeating Arms purchased the patent and manufactured over 500,000 units. The pattern was established early. Browning would conceive a mechanism, build a prototype in his small Ogden workshop, demonstrate it to manufacturers, and sell the design. Between 1879 and 1917, he had invented the pump-action shotgun, the semi-automatic shotgun, the lever-action rifle, the semi-automatic pistol, the blowback-operated firearm, and the recoil-operated automatic weapon. His designs were produced by Winchester, Colt, Remington, Fabrique Nationale, and virtually every major firearms manufacturer in the world. His automatic weapons had revolutionized military thinking. The M1911 pistol, adopted by the U.S. Army in 1911, would serve American forces for 74 years. The Model 1917 machine gun, a water-cooled 30 caliber weapon, was transforming trench warfare in Europe. But Browning, studying reports from the Western Front, recognized these weapons' limitations. Machine guns in 1917 fired rifle-caliber ammunition, typically 30-caliber, 7.62mm rounds. These were effective against infantry, but increasingly ineffective against the war's new realities: armored vehicles, aircraft, reinforced positions. Browning calculated that a 50-caliber round, half an inch in diameter, would deliver approximately 5 times the kinetic energy of a 30-caliber round. But creating a machine gun to fire such powerful ammunition required solving problems that conventional firearms engineering said were unsolvable. The 50-caliber cartridge itself didn't exist in suitable form. The largest machine gun rounds in common use were 30-caliber. Larger caliber weapons existed as single-shot rifles or artillery pieces, but nothing intermediate. Browning collaborated with Winchester and Frankfurt Arsenal to develop what would become the 50 BMG Browning machine gun cartridge. The round was massive, 5.45 inches long, weighing approximately 4 ounces, propelling a 750-grain bullet at approximately 2,800 feet per second with muzzle energy exceeding 13,000 foot-pounds. For comparison, a standard 30-caliber machine gun round generated approximately 2,700 foot-pounds of muzzle energy. Browning's 50-caliber cartridge delivered nearly 5 times that power. The chamber pressure was equally formidable, approximately 55,000 psi, pounds per square inch. No existing machine gun mechanism could handle such forces repeatedly without immediate catastrophic failure. Browning's solution was characteristically elegant and completely unprecedented. He designed a short recoil operation, where the barrel and bolt recoiled together for approximately 3/4 of an inch before the bolt unlocked and continued rearward while the barrel stopped. This absorbed and distributed the tremendous recoil forces across the entire weapon system, rather than concentrating them at a single point. The bolt itself was massive, weighing over 2 pounds, using its own inertia to control the firing cycle. The timing was critical. The bolt had to remain locked during the peak pressure phase, approximately 0.003 seconds after ignition. Unlocking had to occur precisely when chamber pressure dropped to safe levels, approximately 15,000 psi. The bolt had to travel rearward approximately 4 inches, extracting and ejecting the spent cartridge, then travel forward, strip a new round from the belt, chamber it, lock the bolt, and fire, all in approximately 0.1 seconds for a 600 round per minute cyclic rate. This is where the October 1917 prototype had failed. The timing sequence was off by approximately 0.001 seconds, 1,000th of a second. In that infinitesimal discrepancy, chamber pressure was still too high when the bolt unlocked, creating stress that propagated through the entire mechanism until something failed catastrophically. After 47 rounds, the bolt locking lugs sheared, the bolt assembly disintegrated, and the weapon destroyed itself. Browning understood immediately what had happened and how to fix it. The solution required modifying the barrel extension, changing the recoil spring tension, and redesigning the bolt locking mechanism. He returned to his workshop in Ogden and began the redesign. Working 18-hour days through November and December 1917, Browning created detailed drawings of the modified design. His workshop, a modest building behind his home, contained lathes, mills, drill presses, and measuring instruments accurate to thousandths of an inch. He fabricated each component personally, measuring repeatedly, testing fit and function, adjusting dimensions by fractions of a millimeter. By January 1918, the second prototype was complete. It looked substantially similar to the failed first prototype, but incorporated dozens of subtle modifications. The barrel extension was reinforced and lengthened by 0.075 inches. The recoil spring was strengthened by 12%. The bolt locking lugs were redesigned with a different engagement angle and made from stronger steel alloy. Most critically, the timing sequence was adjusted by modifying the cam path that controlled bolt unlock timing. The second test firing occurred February 7, 1918, again at Springfield Armory, but this time with minimal fanfare. Browning, his assistant Burton, and a single Army observer, Captain Charles Hopkins, attended. Hopkins had been one of the few ordnance officers who hadn't completely dismissed the first test as hopeless. He attended primarily from curiosity about whether Browning could actually fix what everyone else considered an unfixable design. The weapon was mounted on a reinforced test stand. A belt of 100 rounds was loaded. Browning himself charged the weapon, stepped back, and nodded to Burton, who would operate the trigger, while Browning observed the weapon's function. Burton pressed the trigger and held it down. The Browning 50 caliber machine gun fired all 100 rounds in 10 seconds without malfunction. The sound was unlike anything Captain Hopkins had heard, a deep, pounding rhythm that he would later describe as sounding like God's own hammer striking an anvil. The kinetic energy was visible in the way rounds struck the target backstop 200 yards distant, each impact sending up clouds of pulverized concrete and metal fragments. When the firing stopped, Burton released the trigger and stepped back. The weapon sat on its mount, barrel glowing dull red from heat, but otherwise intact and functional. Browning approached, examined the mechanism carefully, operated it manually to check function, then turned to Captain Hopkins with an expression of satisfaction. "Captain, I believe this weapon is ready for formal evaluation." Hopkins, still somewhat stunned by what he'd witnessed, managed to respond. "Mr. Browning, I've just seen a machine gun fire 150 caliber rounds continuously. Every other weapon firing cartridges this powerful is either a single-shot rifle or an artillery piece. If this is reproducible, if this weapon can maintain this performance, you've created something unprecedented." "It's reproducible," Browning said simply, "and it will maintain this performance. We'll demonstrate it can fire 1,000 rounds continuously. We'll demonstrate it can be field-stripped and reassembled by an ordinary soldier in under 2 minutes. We'll demonstrate reliability that exceeds any existing machine gun. This weapon will still be in service 100 years from now, Captain. I guarantee it." Hopkins's report to the Army Ordnance Board was enthusiastic, but the institutional response was complicated by timing. February 1918 found the American military fully committed to the final campaigns of World War I. The 30 caliber Browning M 1917 machine gun was being produced as rapidly as factories could manufacture them. Introducing a completely new weapon system, requiring new ammunition, new logistics, new training, seemed impractical with the war reaching its climax. The Ordnance Board authorized continued development and limited testing, but deferred production decisions until after the war. This bureaucratic delay frustrated Browning but ultimately proved beneficial. It gave him nearly 2 more years to refine the design, conducting extensive testing that revealed and solved problems that would have emerged in production. Between February 1918 and November 1919, Browning manufactured 4 more prototype weapons, each incorporating refinements. The barrel was modified to improve heat dissipation. The feed mechanism was redesigned to handle ammunition belts more smoothly. The receiver was strengthened in areas where stress analysis showed potential weakness. The trigger mechanism was simplified for easier maintenance. Most significantly, Browning developed a quick-change barrel system that allowed overheated barrels to be swapped in seconds, solving the biggest limitation of sustained fire weapons. If you're finding this deep dive into firearms engineering and the birth of an iconic weapon fascinating, please subscribe to the channel. We bring you these incredible untold stories of innovation and the individuals who changed military history through sheer brilliance and determination. Hit that subscribe button for more amazing historical content every week. By November 1919, when the formal Army evaluation finally occurred, Browning's 50 caliber machine gun had evolved into a mature weapon system. The official test protocol was punishing, designed by skeptics who still doubted that any weapon could sustain firing 50 caliber ammunition at automatic rates. Test 1. Sustained fire of 1,000 rounds without stoppage. Browning's weapon fired 1,000 rounds in 1 minute and 40 seconds without malfunction. The barrel glowed bright orange from heat but continued functioning perfectly. Test 2. Endurance trial of 10,000 rounds fired in 100-round bursts with 60-second intervals. The weapon completed all 10,000 rounds over approximately 3 hours with only routine maintenance. Barrel changes every 1,000 rounds. 0 malfunctions attributable to weapon design. Test 3. Environmental testing. The weapon was exposed to temperature extremes, from -20 degrees Fahrenheit to +120 degrees. It was submerged in water, caked with mud, exposed to sand. After each environmental exposure, it fired 100 rounds without malfunction. Test 4. Accuracy evaluation. At 500 yards, the weapon placed 80% of rounds within a 20-inch circle. At 1,000 yards, 50% within a 30-inch circle. This accuracy, combined with the 50 caliber round's tremendous kinetic energy, meant the weapon could engage targets effectively at ranges exceeding a mile. Test 5. Penetration testing. 50 caliber armor-piercing rounds penetrated 3/4 of an inch of steel armor at 100 yards, half an inch at 500 yards. They penetrated 18 inches of reinforced concrete. They could destroy engine blocks, penetrate sandbag fortifications, disable armored vehicles, The destructive power was unprecedented for a man-portable weapons system. The formal evaluation report, submitted December 19, 1919, concluded, "The Browning 50 caliber machine gun represents a revolutionary advance in automatic weapons technology. It fires the most powerful cartridge ever adapted to machine gun use, with reliability equal or superior to existing smaller caliber weapons. It is recommended for immediate adoption and production, but peacetime military budgets delayed production." The weapon was officially adopted as the M1921, but actual manufacturing didn't begin until 1923 at a limited rate. Only a few hundred weapons were produced through the 1920s. The design underwent additional refinements, emerging in 1933 as the M2, the version that would become standard. The M2 Browning 50 caliber machine gun weighed 84 pounds without mount or ammunition. It was 45 inches long with a quick-change barrel allowing sustained fire indefinitely as long as barrels were swapped before overheating. Cyclic rate was approximately 550 rounds per minute, though practical rate, accounting for barrel changes and reload, was closer to 40 rounds per minute sustained. Maximum effective range was approximately 2,000 yards, though absolute maximum range exceeded 7,000 yards. The weapon could be mounted on ground tripods, vehicles, aircraft, or watercraft. It could fireball ammunition for general purpose, armor-piercing for armored targets, incendiary for fire-starting effect, armor-piercing incendiary combining both, and tracer rounds for fire control. This ammunition variety made it effective against virtually any target a machine gun might engage. What distinguished the M2 wasn't just its power, but its reliability. The fundamental mechanism Browning designed in 1917-18 remained essentially unchanged through decades of service. The weapon's mean rounds between failure exceeded 10,000 rounds in optimal conditions. It could function in temperatures from -65 to +125 degrees Fahrenheit. It could operate at altitudes from sea level to over 30,000 feet. It could be maintained by soldiers with basic training using simple tools. World War II validated every claim Browning had made about his weapon's revolutionary impact. When the war began in 1939, American forces possessed approximately 20,000 M2 machine guns. By 1945, over 2 million had been manufactured by Colt Buffalo Arms Corporation, Kelsey Hayes Wheel Company, General Motors, and other contractors. The M2 proved devastatingly effective in every role. On the ground, it anchored defensive positions, providing fire support infantry couldn't ignore or assault through. Mounted on vehicles, particularly the famous M16 multiple-gun motor carriage with 4 M2s on a half-track, it created mobile firepower that suppressed enemy positions and engaged aircraft. Mounted on tanks, it provided commanders with long-range anti-personnel capability and could engage thin-skinned vehicles. In aircraft, the M2 truly demonstrated Browning's genius. Fighters, bombers, and reconnaissance aircraft mounted single or multiple M2s. The B-17 Flying Fortress carried up to 13 50 caliber machine guns in various turret and handheld positions. The B-24 Liberator carried 10. The P-47 Thunderbolt fighter carried 8 wing-mounted M2s capable of destroying enemy aircraft or strafing ground targets with equal effectiveness. The air-to-air effectiveness was remarkable. 50 caliber rounds traveling at 2,800 feet per second combined with aircraft closing speeds could exceed 4,000 feet per second of relative velocity, delivering kinetic energy that could literally disintegrate enemy aircraft. A 1-second burst from 8 guns delivered approximately 80 rounds, enough to destroy any aircraft in existence. German and Japanese pilots learned to fear the distinctive sound of 50 caliber fire. Luftwaffe reports consistently noted that American fighters' 50 caliber armament was far more effective than British fighters' rifle caliber machine guns or cannon with limited ammunition. Japanese aircraft, lightly built for agility, were particularly vulnerable. A single 50 caliber hit could sever control cables, destroy engines, or kill pilots through armor that stopped smaller caliber rounds. The ground attack capability was equally impressive. P-47 pilots discovered their 850 calibers could destroy locomotives, trucks, tanks, and buildings. The ammunition mix, typically 1 armor-piercing incendiary followed by 1 tracer, created visible fire that aided accuracy, while the armor-piercing rounds penetrated targets and the incendiary component started fires. Trains hit by 50 caliber fire didn't just stop, they exploded. Trucks didn't just break down, they burned. This psychological impact was as important as physical destruction. Statistical analysis showed the M2's effectiveness clearly. In the Pacific Theater, American fighters achieved approximately 1.2 kills per fighter lost in air combat. Similar Allied fighters with different armament achieved approximately 0.8. The difference was attributed primarily to the M2's superior hitting power. A pilot could score kills with fewer hits, compensating for limited accuracy and high-speed combat. In Europe, ground forces calculated that a single M2 position could suppress or deny access to an area approximately 800 yards deep and 400 yards wide, essentially creating a no man's land that enemy infantry couldn't cross. This area denial forced enemies to either bypass the position, exposing their flanks, or concentrate forces for assault, creating targets for other weapons. The versatility was unprecedented. The same basic weapon served effectively in desert, jungle, Arctic, mountain, and urban environments. It functioned in roles from anti-aircraft defense to anti-vehicle, to anti-personnel to anti-structure. It operated from aircraft flying at 300 miles per hour at 30,000 feet and from fixed ground positions. This universality meant simplified logistics, training, and maintenance across the entire military. Korea and Vietnam further proved the M2's enduring value. In Korea, M2s mounted on vehicles provided mobile fire support during rapid advances and retreats. Defensive positions anchored by M2s held against massed Chinese attacks that overran positions lacking heavy machine gun support. The weapon's ability to engage targets at extreme range proved critical in the mountainous terrain, where engagements occurred at distances exceeding normal rifle range. Vietnam saw innovative M2 applications. Helicopters mounted M2s as door guns, providing fire support for insertions and extractions. River patrol boats mounted multiple M2s, creating formidable firepower for interdicting enemy supply lines. Forward observers called for M2 fire against enemy positions, using the weapons like precision artillery. The tracer rounds' visibility allowed adjustment of fire even at night. The M2's reliability in Vietnam's harsh environment exceeded newer weapons. While the M16 rifle initially suffered reliability problems in jungle conditions, the M2 functioned flawlessly in mud, humidity, and heat. Units that had access to M2s used them preferentially because soldiers trusted weapons that always worked. Before we explore how this 90-year-old design remains in service today, if you haven't subscribed yet, please hit that button now. These stories of innovation and engineering excellence that changed history deserve to be told and remembered. Join our community for more incredible historical content. The M2's longevity is unparalleled in military history. Weapons typically become obsolete within decades as technology advances. The M2 has served continuously since 1933, 90 years and counting. Modern M2s in current service are fundamentally identical to weapons manufactured in World War II. Parts are interchangeable across nearly a century of production. This longevity stems from Browning's original design brilliance. He didn't design a weapon for World War I technology. He designed a weapons system optimized around fundamental physics and mechanical principles that don't change. The .50 caliber cartridge's ballistics remain effective against modern threats. The mechanism's reliability remains superior to many newer designs. The weapon's versatility means it remains relevant despite changing tactical requirements. Modern upgrades have been minimal and additive rather than replacing core design. Quick change barrel handles were redesigned for easier operation. Soft mounts replaced rigid mounts to reduce vibration. Optical sights supplement iron sights, but the fundamental mechanism remains Browning's original design. This is extraordinary. Imagine using a computer designed in 1933, or flying an aircraft designed then, or communicating with radios designed then. Yet the military uses machine guns designed then because Browning's design was that good. Current American military forces maintain approximately 40,000 M2s in inventory. Every branch operates them. Infantry, armor, aviation, special operations all depend on Browning's design. The weapon that Army officers called ridiculous in 1917 remains standard equipment in 2023. Allied nations operate tens of thousands more. The M2 serves with military forces in over 100 countries. Total production across all manufacturers and nations exceeds 3 million units. It's been manufactured under license in Belgium, Japan, Turkey, and other nations. Some nations have operated M2s continuously for over 70 years. The combat record is staggering. The M2 has participated in every American military conflict from World War II through Afghanistan and Iraq. It's been fired in anger on every continent except Antarctica. It's operated from every environment imaginable. Arctic tundra to tropical jungle to mountain peaks to desert wastes to urban streets. It's been mounted on hundreds of different platforms, from jeeps to tanks to helicopters to boats to fixed fortifications. Conservative estimates suggest M2s have fired over 10 billion rounds in combat and training since 1933. They've destroyed tens of thousands of vehicles, aircraft, and structures. They've provided fire support for millions of soldiers, sailors, airmen, and Marines. The lives saved by M2 fire support, enemy attacks suppressed or broken, positions held, medevacs covered, are literally incalculable. John Moses Browning died November 26, 1926, in Liège, Belgium, while working on yet another firearms design at age 71. He didn't live to see World War II, Korea, Vietnam, or the modern era. He never witnessed his .50 caliber design's full impact on military history. But he had known, standing in that testing room in February 1918, watching 100 rounds fire flawlessly, that he'd created something unprecedented. His son, Val Browning, continued development work, overseeing the refinements that produced the M2 variant. The Browning family maintained connection to Colt and Fabrique Nationale, the primary manufacturers, but the fundamental achievement was John's alone. One man, working in a modest workshop in Ogden, Utah, conceived and created the mechanism that would become history's most successful heavy machine gun. The technical achievement deserves emphasis. Browning designed the M2 using slide rules, paper calculations, and intuition. No computers, no finite element analysis, no computational fluid dynamics, no computer-aided design. He calculated recoil forces, chamber pressures, bolt velocities, timing sequences, all by hand. He fabricated prototypes using manual machine tools, measuring with mechanical micrometers and calipers. The precision he achieved with this limited technology speaks to extraordinary mechanical intuition. Modern engineers, analyzing Browning's design with advanced computational tools, consistently conclude the mechanism is nearly optimal. Attempts to improve it using modern design methods produce minimal gains. The barrel's dimensions, the bolt's mass, the recoil spring tension, the timing sequences, all prove to be at or near theoretical optimum for the design requirements. Browning achieved through intuition what modern engineers struggle to match with computers. The .50 BMG cartridge itself remains in widespread use beyond the M2. Sniper rifles chambered in .50 BMG engage targets at distances exceeding 2 miles. Anti-material rifles use .50 BMG to disable vehicles and equipment. The round's effectiveness hasn't diminished despite being over 100 years old. Modern ammunition uses improved propellants and projectiles, but the fundamental cartridge dimensions remain Browning's original 1918 design. The human element of Browning's achievement matters. He wasn't a formally trained engineer with advanced degrees. He was a largely self-educated gunsmith who learned through experimentation and observation. His education consisted of years in his father's shop, building and repairing firearms, studying mechanisms, understanding how materials and forces interacted. This practical foundation proved superior to theoretical training in creating functional weapons. Browning understood instinctively how mechanisms would behave under stress because he'd built hundreds of mechanisms and observed their failures. When the 1917 prototype exploded, he didn't need extensive analysis to understand why. He'd seen similar failures in other designs and recognized the timing discrepancy immediately. His workshop approach was methodical but intuitive. He would build a mechanism, test it, observe how it failed, modify the design, test again. He repeated this cycle until the mechanism worked reliably. This empirical approach, testing and refining based on observed behavior rather than theoretical predictions, produced designs that worked under real-world conditions that theory didn't fully capture. The ridiculous idea that others mocked, firing .50 caliber rounds from an automatic weapon at high cyclic rates, succeeded because Browning trusted his own judgment over conventional wisdom. Experts said it couldn't be done. Calculations showed the recoil forces would destroy any mechanism. Military officers declared the concept fundamentally unsound. Browning ignored them all and built a weapon that worked. This confidence came from decades of success. By 1917, Browning had already invented multiple revolutionary firearm designs. He knew his abilities. When observers said something was impossible, Browning heard a challenge. The .50 caliber machine gun was impossible only until he made it work. Then it became the standard against which all other heavy machine guns were measured. The impact on military doctrine was profound. Before the M2, machine guns were primarily defensive weapons, holding fixed positions. The M2's reliability, accuracy, and effectiveness made it equally valuable offensively. Units with M2s could suppress enemy positions during advances. They could provide overwatch fire for maneuvers. They could engage targets at ranges where enemies couldn't effectively return fire. The psychological impact shouldn't be underestimated. Soldiers on the receiving end of .50 caliber fire describe it as terrifying. The sound of rounds passing overhead is distinctive and unmistakable. The visible impact of rounds, the way they destroy structures and vehicles, creates immediate understanding that the fire must be avoided. This suppressive effect, forcing enemies into cover and limiting their actions, multiplies the M2's tactical value beyond simple casualty infliction. Modern military forces attempting to replace the M2 have consistently failed to field superior alternatives. Numerous programs have tried developing improved heavy machine guns using modern materials, manufacturing techniques, and design methods. Most have been abandoned after testing showed minimal improvement over the 90-year-old Browning design. Those that did enter production typically supplement rather than replace the M2. The M240, introduced in 2010, incorporated a quick-change barrel system improved from the original design. It was billed as the M2's replacement. Today, both variants serve alongside each other because neither is definitively superior for all applications. The fundamental Browning mechanism remains unchanged in both. This speaks to the original design's excellence. Browning created a weapon so well optimized for its role that a century of technological advancement can't significantly improve it. The materials are better, the manufacturing is more precise, the accessories are more sophisticated, but the core mechanism remains his 1918 design. The lessons from Browning's achievement extend beyond firearms. He demonstrated that transformative innovation often comes from challenging fundamental assumptions. Everyone assumed .50 caliber machine guns were impossible because nobody had questioned whether the assumptions behind that conclusion were valid. Browning questioned everything, tested assumptions, and proved the impossible was merely difficult. He showed that practical experience can outweigh theoretical training. The formally educated engineers at Army Ordnance and major manufacturers said it couldn't be done. The self-taught gunsmith from Utah did it. This pattern repeats throughout technological history. The person closest to actual hardware, actually building and testing, often sees solutions theorists miss. He proved that elegant simplicity beats complex sophistication. The M2 mechanism is remarkably simple, comprising fewer than 100 parts. Modern weapons often contain hundreds of parts. Yet Browning's simple design has proven more reliable than many complex modern alternatives. Simplicity means fewer failure points, easier maintenance, better battlefield reliability. Most importantly, he demonstrated the value of persistence combined with confidence. The October 1917 prototype failure would have ended most projects. Browning treated it as a data point. The Army said it was impossible. Browning built it anyway. Experts mocked it as ridiculous. Browning proved them wrong. This refusal to accept others' limitations on what was possible drove him to create designs that changed history. Today, a soldier manning an M2 in Afghanistan or Iraq operates a weapon fundamentally identical to those used by soldiers in World War II, Korea, and Vietnam. That soldier is firing a mechanism conceived in the mind of a Utah gunsmith over a century ago, designed using tools and methods from an era before computers, proven reliable across 9 decades of service in every imaginable environment and condition. That continuity, that unbroken chain connecting modern warfare to Browning's workshop, represents something profound about quality engineering. Build something truly excellent, optimized not for current technology, but for fundamental principles, and it endures. The M2 Browning .50 caliber machine gun has endured longer than any other military weapon system still in frontline service, precisely because Browning built it right the first time. The gunsmith's ridiculous idea, the impossible machine gun that experts said couldn't work, became the most successful heavy machine gun in history. It fired over 10 billion rounds in combat. It served continuously for 90 years without substantial modification. It operates in over 100 countries. It remains standard equipment across American forces. And it all started with one man standing before a destroyed prototype, seeing not failure, but possibility, and having the brilliance and persistence to turn that possibility into reality. John Moses Browning's legacy is measured not in patents or profits, but in the weapon that still bears his name after nearly a century. Every M2 firing today proves his 1917 vision correct. Every soldier whose life was saved by M2 fire support validates his persistence. Every military that depends on his design demonstrates its enduring excellence. The ridiculous idea worked. And 90 years later, nothing has improved on what Browning created in a small workshop in Utah, armed with genius, determination, and absolute confidence that what everyone else called impossible was merely very, very difficult. The M2 Browning 50 caliber machine gun stands as testament to what one individual with vision and skill can achieve, and as proof that truly excellent design transcends the technology of its era to serve across generations.